Come to problem number 6, test 3 extras. The question says, find the average kinetic energy and velocity of a helium atom at a temperature of 25 degrees Celsius. So what's the average kinetic energy of that helium atom and what is its velocity? The equation for this is the kinetic energy, the average kinetic energy per molecule or per atom is equal to 1/2 the mass of that atom times the velocity of the atom squared, and then the average of that. So basically you're doing half the mass of the atom times the velocity of the atom squared, then take average of that, and that's equal to 3/2 kT, where again temperature is measured in Kelvin, and 3/2 kT because we're assuming the molecule has 3 degrees of freedom, going right, going up and down, and going back and forth. Okay. So K is equal to Boltzmann's constant, which is equal to 1.38 times 10 to the minus 23 joules per Kelvin. So it has a units of joules per Kelvin, so that when you multiply it by Kelvin, you're gonna get units of energy, right? So what's the average kinetic energy of this helium atom? So we have kinetic energy average is equal to, well, for now we could just calculate this one, 3/2 times 1.38 times 10 to the minus 23. Temperature of 25, again we have to convert to Kelvin, 273.15 plus 25. So the average kinetic energy of each molecule is going to be very small. So times 1.5, that gives you 617.17 times 10 to the minus 23, and that's joules. And I can convert to, go back to spaces, so 6.17 times 10 to the minus 21 joules. Okay? Okay, so now what if I wanted to calculate the what is the average velocity of the molecules, okay, of the helium atom? Well, how am I going to do that? Well, I'm going to say V squared average is equal to, so the half and the half cancel, it's equal to 3 kT divided by the mass of each particle, each helium particle, right? So we could either use this version, but the more commonly used version is a little bit different. Here's what I'm going to argue. I say, what's the kinetic energy for a number of molecules, an n number of molecules? So kinetic energy per n molecules. Okay, so what am I going to have to do? Well, I'm going to have to multiply this by how many molecules there are, right? Because these are how many, this is the energy per molecule, multiply it by n. So 1/2 n mv squared average, right? So I want to know what's the total kinetic energy per n number of molecules. Okay, well that's going to equal 3/2 knt, or we can say nkt, right? Well, here's one of the things we know. We know that the number of molecules, n, is equal to what? The number of moles times Avogadro's constant, right? Avogadro's constant, it tells you that is equal to 6.02 times 10 to the 23. So it says every mole of an atom or molecule or whatever it is, a unit, every mole has that many molecules or atoms, right? So if you multiply molecules per mole by number of moles, what do you get? Number of molecules, right? So then we end up getting here what? N molecules is going to be what? 3/2 knt. Okay, and then make the n is equal to number of moles times Na times T. And then that's equal to what? 1/2 nmv squared, right? 1/2 nmv squared average. Okay? Now, take the n divided into this. Okay, divide the n into here. What do you get? Well, this is the total number of mass of n number of molecules, right? This is the total mass. You divide it by the number of moles, what do you get? You get the molar mass, right? In other words, how much mass is there divided by how many moles there are? Well, that's the molar mass, which we call big M, right? 1/2 big M V squared average. This is known as molar mass, which tells you how many grams per mole, which you can get from the periodic table, right? Helium molar mass is 4 grams. Every mole of helium has a mass of 4 grams. So what is this going to be equal to? Well, this is going to be 3/2 n times k. What is that? Well, that's our gas constant, right? RT. So this is a much better format to use. Why is that the gas constant? Well, let's show you here. K was, remember, 1.38 times 10 to the minus 23. What is Avogadro's constant? 6.02 times 10 to the 23. You can see they cancel out here, and you get what? 1.38 times 6.02. What is that equal to? That's equal to 8.31. So that's equal to what? Na times K. So Avogadro's constant times Boltzmann's constant, right? Avogadro's number times Boltzmann's constant, that's equal to our gas constant R, which we know as 8.31. So this equation then becomes what? RT, which is going to equal 1/2 molar mass V squared average, right? So this time we don't need the mass of each particular molecule. We just need the molar mass and the gas constant. So if I want to know the square average, V squared average, that's equal to what? The 2 and the 2 are going to cancel, 3RT over M, and then square root that, you get the average velocity of each molecule, right? So let's calculate it here. 8.31 times the temperature is equal to what? 25 Celsius, so that was what? 273 plus 25, 298.15 divided by the molar mass. So here's what we use. 1 mole of helium, right? 1 mole of helium is 4 grams. So you got to do 0.004 kilogram. You got to convert it to kilogram here. 0.004. Okay, so do this. So we get a speed of 1,363 meters per second. So at a temperature of 25 Celsius, average velocity of the molecule of the helium atom is 1,363. What would it be for the hydrogen atom? Okay, for the hydrogen atom, the molecular mass is 0.001. 4 times lighter, right? So, well, if you take the square root of 4, you get 1/2, right? So basically, the number in the bottom is smaller by 1/4. If you take square root 1/2, and then you go, it goes to the top, so it's going to be double. So I predict when we calculate it, it's going to be double this speed. 3 times 8.31 times 298.15 divided by 0.001. So it's going to be exactly double the hydrogen atom, 2726.33 meters per second, which is exactly double that. The heavier the molecule, like let's say oxygen, which is O2, right? Well, that's going to be 32, right? Atomic weight. Then you have carbon dioxide or other molecules. The heavier the molecule, the slower it is going to be going, okay? This has a lot to do with temperature that the planet can retain. Like one of the reasons Mercury doesn't have an atmosphere is because it is too hot and it is too small. So its escape velocity is very low, and its molecules are going too fast. So it has lost most of its atmosphere due to seeping to the solar system, okay? So this is a very important topic, particularly in the realm of astronomy and atmospheres of planets. Okay, thank you.